Good morning, afternoon, or evening, everyone. Thank you for joining me today. Over the next 20 minutes, we're going to explore the fascinating world of hidden watermarks and how artificial intelligence is revolutionizing this technology. We'll start with a brief introduction to set the context, then dive into what watermarking actually is and why it matters. I'll walk you through the key distinction between viewable and hidden watermarks, which is really the core of what we're discussing today. Then we'll explore the different approaches to hidden watermarking. We'll look at traditional methods that have been around for years, the newer AI-based techniques that are transforming the field, and hybrid approaches that combine the best of both worlds. After that, we'll examine how AI-based watermarking works across different media types, text, images, and videos, because each presents unique challenges and opportunities. We'll weigh the pros and cons of these different methods so you can understand their practical applications and limitations. To make this concrete, I'll show you a live demonstration of watermarking in action. And finally, we'll wrap up with time for your questions and discussion. Let's get started. So let's start with the fundamentals. What exactly is watermarking? At its core, watermarking is the process of embedding a marker, essentially a digital signature or identifier, into digital content. And when I say digital content, I mean across the board: text documents, images, videos, and even audio files. The purpose of this embedded marker is multifaceted. It can indicate ownership, essentially saying, "This belongs to me." It can verify authenticity, proving that content is genuine and hasn't been tampered with. And it can track distribution, allowing creators to see where their content travels across the internet. Now, here's where it gets interesting. Watermarks come in two main flavors, and understanding this distinction is crucial. First, we have visible watermarks. These are the ones you're probably already familiar with. Think about stock photography websites like Shutterstock or Getty Images. They plaster their logos right across the image. Or news organizations that put their branding in the corner of video footage. These are obvious, intentional marks designed to be seen. They're meant to deter unauthorized use because, let's face it, nobody wants to use an image with a giant logo across the middle. But then we have hidden watermarks, and this is where the technology becomes really sophisticated. These are imperceptible changes embedded into the content, modifications so subtle that the human eye or ear cannot detect them. You could look at a watermarked image and one without a watermark side by side and see absolutely no difference. Yet, the marker is there, encoded in the data itself, waiting to be detected by specialized algorithms. This invisible approach is particularly powerful because it doesn't degrade the user experience while still providing robust protection and tracking capabilities. And that's what we're going to focus on today. Now that we understand what watermarking is, let's dig deeper into these two distinct approaches and really understand when and why you'd use each one. Let's start with viewable watermarks, since they're the more straightforward of the two. These are clearly visible overlays, things like logos, text, or patterns that are intentionally placed on top of your content. You've seen these everywhere. When you browse stock photo sites, that diagonal text saying sample or watermark across the image. That's viewable watermarking in action. News agencies like CNN or BBC place their logos in the corner of broadcast footage. Photographers often stamp their name or logo on preview images before a client purchases the full resolution version. The use cases here are pretty clear-cut. First, copyright protection. You're making it very difficult for someone to use your content without permission because that visible mark degrades its value. Second, branding. Companies use this to maintain visibility and ensure their mark travels with their content. And third, proof of authenticity. News organizations use visible watermarks to verify that footage is genuinely from their reporters in the field. Now, hidden watermarks are a completely different beast. These are imperceptible marks, embedded deep within the content using sophisticated techniques, frequency domain manipulation, strategic pixel modifications, or cutting-edge AI algorithms. The beauty here is that you cannot see them with the naked eye. A watermarked 4K image looks identical to the original, yet it carries a unique signature. Where do we use these? Copyright enforcement is huge. Companies like Adobe and Digimarc use hidden watermarks to track copyrighted material across the internet. If someone steals your image and posts it elsewhere, you can prove ownership even if they've cropped or modified it. Content integrity verification is another critical application. Well, think about deepfakes and AI-generated content. Hidden watermarks can prove whether a video has been manipulated or generated by AI. Major AI companies like OpenAI and Google are now exploring watermarking their generated content to combat misinformation. And then there's covert tracking. Media companies embed unique watermarks in each distributed copy of content, like different versions sent to different theaters or streaming platforms. If a movie leaks online, they can trace exactly which copy was the source. It's like a fingerprint that follows the content wherever it goes, invisible but traceable. The key difference: viewable watermarks prioritize deterrence and visibility. Hidden watermarks prioritize forensics and tracking without compromising the content's appearance or user experience. All right, now we get into the really technical and fascinating part. How do we actually embed these hidden watermarks? There are three main approaches, each with its own strengths and ideal use cases. Let's start with traditional methods, which have been the backbone of watermarking technology for decades. First up is frequency domain watermarking. This is actually quite elegant. Instead of working directly with the image or audio as you see or hear it, we transform it into the frequency domain using mathematical techniques like DCT, discrete cosine transform, or DWT, discrete wavelet transform. Note, if you've ever heard of JPEG image compression or MP3 audio compression, you're already familiar with these concepts because they use the same underlying math. What we do is embed the watermark by carefully altering these frequency components or coefficients. The beauty of this approach is that changes in the frequency domain are much less noticeable to human perception than direct changes to pixels or audio samples. It's robust against common operations like compression and filtering. Then we have pixel domain methods, which work more directly. LSB substitution, least significant bit substitution, is probably the simplest example. Imagine a pixel with a value of 152. In binary, that's 10,011,000. The last bit, the least significant bit, contributes almost nothing to the overall color. We can flip it from 0 to 1 or vice versa, and your eye won't notice the difference. By systematically modifying these LSBs across the image, we can embed substantial amounts of data invisibly. Spread spectrum techniques take this further by distributing the watermark across many pixels, making it even more robust and harder to remove. And we can't forget metadata embedding. This is perhaps the simplest approach. We're not actually modifying the visual or audio content at all. Instead, we're writing information into the file's metadata tags. For images, that's EXIF or XMP data. For audio, it's ID3 tags. While this method doesn't alter the content itself, it's also the easiest to strip away. Anyone can simply remove metadata, so it's less secure but incredibly easy to implement. Now let's talk about AI-based methods, which represent the cutting edge of watermarking technology. Deep learning and neural networks have revolutionized this field. Instead of relying on handcrafted algorithms, we train neural networks to learn how to embed and extract watermarks optimally. What makes this remarkable is that these AI models can create watermarks that are incredibly resilient. They can survive aggressive JPEG compression, cropping, rotation, color adjustments, even screenshots and re-photographs of screens. The network learns to hide information in patterns that persist through these transformations. Companies like Google and Meta are investing heavily in this approach, especially for watermarking AI-generated content to combat deepfakes and misinformation. Finally, we have hybrid approaches that combine multiple technologies for enhanced security. One of the most innovative combinations is using zero-knowledge proofs, ZKP, alongside blockchain technology. Here's why this is powerful. With zero knowledge, proofs, you can verify that you own a watermark without actually revealing what the watermark is or where it's hidden. It's cryptographic magic that proves ownership secretly. Then, when you combine this with blockchain, you get an immutable, tamper-proof record of watermark ownership stored across a distributed ledger. No single entity can alter this record. This approach is gaining traction in high-value digital art markets, NFTs being a prime example, where proving authentic ownership and provenance is absolutely critical. Each of these approaches has its place. Traditional methods are well understood and computationally efficient. AI-based methods offer superior robustness and adaptability, and hybrid approaches provide the highest level of security for high-stakes applications. The choice depends on your specific needs, what content you're protecting, what threats you're defending against, and what resources you have available. One of the most exciting aspects of AI-based watermarking is how adaptable it is across completely different types of media. Each medium, text, images, and video, presents unique challenges, and AI has developed sophisticated solutions for each one. Let's explore how this works. Starting with text watermarking, which is perhaps the most challenging because text is discrete, and any obvious changes can break meaning or grammar. This is where AI really shines. We can retrain language models, think get-style models, to subtly modify word choice, sentence structure, or syntax in ways that are virtually undetectable to human readers. For example, the quick brown fox versus the swift brown fox. Same meaning, different words. The AI learns which substitutions preserve meaning while encoding information. But it goes beyond just word choice. AI models can introduce subtle spacing patterns, maybe adding an extra microscopic space here or adjusting kerning there. They can use nearly imperceptible font variations or substitute visually identical Unicode characters. For instance, there's a regular letter E and a Cyrillic Y that look identical but have different character codes. An AI can strategically place these throughout a document to create a unique fingerprint. This is particularly valuable for tracking leaked documents or identifying AI-generated text. Companies like OpenAI are actively researching this to watermark ChatGPT outputs, which could help educators identify AI-written essays or help content platforms manage synthetic content. Moving to images, this is probably the most mature application of AI watermarking. Neural networks are trained to embed watermarks into both the frequency domain and the pixel domain simultaneously, but they also work with latent features, the deep, abstract patterns that neural networks naturally understand. Here's what makes AI superior to traditional methods. A traditional watermark might break if you crop 30% of an image or compress it heavily. But an AI-trained watermark learns to distribute itself across the entire image in a way that survives these attacks. Google's SynthID is a great example. It can watermark AI-generated images from their IMAIN model in ways that persist even after screenshots, filters, and edits. The neural network learns to hide the watermark in the fundamental structure and patterns of the image, not just in specific pixels or frequencies. It's like the difference between writing your name in sand versus embedding your DNA in every cell. One washes away easily. The other persists no matter what you do to the organism. Now, video watermarking takes this complexity to another level because we're dealing with temporal dimensions, time and motion. AI-based video watermarking works in two primary ways. First, there's frame-by-frame embedding, where each individual frame gets watermarked, similar to images. But the AI ensures consistency across frames, so the watermark doesn't flicker or become detectable through frame comparison. Second, and more sophisticated, is temporal domain modification. Here, the watermark is hidden in the changes between frames, in the motion itself. Think about it. Video is really just a sequence of differences. The AI can encode information in how objects move, how scenes transition, or how lighting changes over time. This temporal approach is incredibly robust. You can re-encode the video, change the frame rate, even crop or resize it, and the watermark persists because it's embedded in the motion patterns themselves. Netflix and other streaming platforms are exploring these techniques to combat piracy. Each stream could carry a unique temporal watermark identifying the account that accessed it. If that movie shows up on a pirate site, they can trace it back to the source, even if it's been re-recorded with a camera pointed at a screen. The real power of AI in all these media types is adaptability. Traditional algorithms follow fixed rules. AI learns. It can adapt its embedding strategy based on the specific content, finding the optimal places to hide information where it's most imperceptible yet most resilient. It's not just following a recipe, it's making intelligent decisions for each unique piece of content. Now that we've explored all these different watermarking methods, let's take a step back and objectively evaluate each approach. Because in the real world, there's no one-size-fits-all solution, you need to choose the right tool for the job. Let's walk through each method and understand the trade-offs. Starting with viewable watermarks, these are your quick and straightforward solution. The pros are obvious. They're incredibly easy to implement. You don't need sophisticated algorithms or deep learning models. Just overlay your logo or text on the content and you're done. And as a visible deterrent, they work well for discouraging casual theft. Someone browsing for images isn't going to use one with a giant watermark plastered across it. But here's the critical downside. They can be removed via editing. Anyone with basic Photoshop skills or content-aware fill tools can clone them out, crop around them, or simply cut them off. And of course, they degrade the viewing experience. Nobody wants to look at an image or watch a video with distracting overlays. So while viewable watermarks are great for previews or low-security scenarios, they're not suitable when you need robust protection. Moving to traditional methods, frequency and pixel domain techniques. The big advantage here is simplicity and widespread adoption. These methods are well understood, well documented, and have been battle-tested for decades. They're computationally inexpensive, so you can watermark thousands of images quickly without needing GPU clusters. Many existing tools and libraries already support these techniques out of the box. However, they're vulnerable to compression and attacks. If someone saves your JPEG at a lower quality, or runs it through filters, or crops and resizes it, your traditional watermark might degrade or disappear entirely. Sophisticated attackers who understand these algorithms can specifically target and remove these watermarks. It's a bit like a standard lock. It keeps honest people honest, but a determined thief with the right tools can break through. Now, AI-based methods represent the cutting edge, and their strength is robustness and adaptability. These neural network-based watermarks can survive aggressive transformations. Crop it, compress it, filter it, screenshot it, the watermark persists. And because the AI learns optimal embedding strategies for each type of content, it's incredibly adaptive. It finds the sweet spot between invisibility and resilience. But there's a significant trade-off: computational expense. Training these neural networks requires substantial computing power. We're talking GPUs running for hours or days. Even the inference step, actually embedding the watermark, is slower than traditional methods. And you need expertise in machine learning to implement and maintain these systems. For a small business or individual creator, this might be prohibitively expensive or complex. It's powerful, but it's not accessible to everyone. Metadata-based watermarking has some really appealing characteristics. It doesn't alter the content at all. The pixels or audio samples remain completely untouched. This means zero quality degradation. It's also lightweight and incredibly easy to implement. Any programming language has libraries for reading and writing metadata. You can watermark 1 million files in minutes, but the fatal flaw is that it's easily removed and lost during format conversion. Anyone can strip metadata with a single command or by simply taking a screenshot. Convert a JPEG to PNG? Metadata might not transfer. Upload to social media? Most platforms automatically strip metadata for privacy reasons. So while metadata watermarking is great for low security tracking or adding attribution that you hope people will preserve, it's useless against anyone actively trying to remove it. Finally, hybrid approaches combining zero-knowledge proofs and blockchain offer the ultimate in security. You get tamper-proof ownership records that are cryptographically secure and distributed across a blockchain. No single entity can alter the record, and you can prove ownership without revealing sensitive details about the watermark itself. This is ideal for high-value digital assets. Think rare digital art, official government documents, or sensitive intellectual property. The downside? Complex implementation. You're now dealing with blockchain infrastructure, cryptographic protocols, and distributed systems. This requires specialized expertise and ongoing maintenance. It's also slower and more resource-intensive than other methods. For most everyday use cases, this level of security is overkill. But when the stakes are high and you absolutely cannot afford to have ownership disputed, hybrid approaches are worth the investment. So the key takeaway here is that your choice of watermarking method should be driven by your specific needs. What's your threat model? What's your budget? What's the value of the content you're protecting? Low security needs? Viewable or metadata? Medium security with broad compatibility? Traditional methods? High security with budget for infrastructure? AI-based? Absolute maximum security for high-value assets? Hybrid approaches. There's a place for each of these in the watermarking ecosystem. Alright, let's see in action with a demonstration using pre-trained neural network model called Stable Signature by Meta. I'm going to walk you through what's happening here in plain English, so don't worry if you're not a programmer. This is actually quite straightforward. First, we load an image, in this case, a classroom photo. We prepare it by making sure it's the right size and format for our AI model to work with. Think of this like preparing a canvas before painting. Next, we create our secret message. This could be random data, or it could be text like, Copyright 2025, converted into binary code, just ones and zeros. This is what we're going to hide inside the image. Now comes the magic, the encoding step. We feed both the image and our secret message into our trained AI model, which we call the encoder. The AI figures out exactly where and how to hide those ones and zeros in the image's pixels in a way that's completely invisible to your eyes. Out comes our watermarked image. To verify the quality, we calculate something called PSNR, peak signal-to-noise ratio. Without getting too technical, this is just a number that tells us how similar the watermarked image is to the original. A higher number means better quality. Typically, anything above 35 or 40 is considered imperceptible to human vision. Then we display three images side by side: the original, the watermarked version, and the difference between them amplified so you can actually see where the changes occurred. Spoiler alert: when you look at the original and watermarked images, you won't be able to tell them apart. Here I am using the word Pearson as watermark. Now for the real test. Can we get our message back? We take the watermarked image and run it through our decoder model. This AI has been trained to find and extract those hidden ones and zeros, even if the image has been slightly modified. Finally, we calculate the accuracy. What percentage of our message bits were correctly recovered? In a good system, you should see 95% to 100% accuracy, meaning our secret message survived the embedding process perfectly. Here the accuracy is about 43.4, which is not very good, which indicates this model requires more training and fine-tuning. And that's it. In just a few seconds, we've hidden information in an image, verified it's invisible, and proven we can reliably extract it. Pretty powerful stuff. Well, that brings us to the end of our presentation today. We've covered a lot of ground, from the basics of what watermarking is, to the cutting-edge AI techniques that are reshaping how we protect and track digital content across text, images, and video. I hope this has given you a solid understanding of the landscape and perhaps sparked some ideas about how these technologies might be relevant to your own work or interests. I want to thank you all for your attention and engagement today. Whether you want to dive deeper into something we covered, explore specific use cases, or discuss the future of this technology, I'm here for it. The forum is now open for questions.